So let's do an example problem in applying Bernoulli's equation. So first let me remind you Bernoulli's equation we derived in a previous video. It says that pressure doesn't just vary with depth for fluids in motion, it varies with depth and changes in speed. So the pressure at any one point in an enclosed fluid system plus density times gravity times height at one position plus 1/2 density times speed at that one position squared is equal to, well, all those same quantities at another point. So if you pick 2 points in a pipe, the sum of pressure, density times gravity times height, and a term that's something like kinetic energy, instead of 1/2 mv squared, it's 1/2 rho v squared. So it's kind of like kinetic energy per unit volume. Anyway, there it is. That's Bernoulli's equation. And so the example problem we have here is with a drinking fountain. Okay, now let's say that you turn on the drinking fountain by pushing the button, and the city engineers designed this so there's too much pressure in the main feeder pipe that brings water to the exit hole. And so it's one of these drinking fountains that when you turn it on, the water comes squirting out of here at a pretty high speed and travels beyond the bowl that it's supposed to flow into. So let's say, for example, that the water acts as a projectile, and we've got to figure out what's the speed that it comes out of here. So let's say the water, when it returns to the same height that it exited from, travels a range of, how about 90 centimeters? And we'll say it comes out of here angled at 42 degrees. So actually the first part of this example problem, if we call this point number 2, here let's draw this again down below. Yeah, we can see there's the feeder pipe, water flows this way through a cross-sectional area number 1, flows uphill, and then exits at point number 2, where the cross-sectional area is much smaller. And so we need to figure out what's the speed that the water exits at point number 2. And that's just a review of projectile motion from earlier in the semester. So hopefully you can recall an equation that says when a projectile returns to the same elevation it left from, that horizontal range can be calculated by taking velocity squared multiplied by the sine of double the angle divided by g. So if we rearrange that equation, velocity squared is rg over sine 2 theta. Grab a calculator, see what you get. If we say it's a range of 0.9 meters, it's the same thing as 90 centimeters, times 9.8 meters per second squared, divided by the sine of, if the angle is 42 degrees, then double that angle would be 84 degrees. I'll give you a minute to punch those numbers into your calculator and see what you get. So that should come out to about 8.869 roughly. Now what are the units? Meters squared per second squared. So that doesn't give us the speed, that gives us speed squared. So to get the speed, we have to take the square root of that. And hopefully your calculator has about the same thing mine says, of pretty much 3 meters per second if we round up. Okay, so let's take this problem to the next level and see if you can derive this equation. The question goes, what's the gauge pressure in the feeder pipe? So one thing we know is when you push this button in, it opens up a valve and it exposes the opening to a pressure of exactly 1 atmosphere. Now let's say, for example, the drinking fountain is, or at least the hole where the water comes out, is 1.7 meters above the ground. And then for the sake of argument, we'll say that the feeder pipe sits below ground at a depth of exactly 1 meter. So now that we found the water flies out of here with a speed of 3 meters per second, can we use that information to figure out what's the gauge pressure down in the feeder pipe? So even though we have some numerical values that we can apply, let's see if we can just derive algebraically a general expression that'll tell us what the gauge pressure is in a feeder pipe in a problem like this. So there's the goal. See if we can derive this equation. Now, R2 and R1 represent the radius of the pipe. So let's say, well, if I give you the diameter, you could figure out the radius. Let's say this pipe has a diameter at down in the feeder pipe with a value of, maybe 10 centimeters. And then we'll say the diameter of the exit hole is about 1.2 centimeters. So don't forget we have this thing known as the equation of continuity. It says A1V1 equals A2V2. So if the pipe is getting constricted because the diameter of the exit hole is much less than the diameter of the feeder pipe, then that's going to play into changes in velocity between point 1 and point 2 in our system. So again, starting with Bernoulli's equation, P1 plus rho g y1 plus 1/2 rho v1 squared equals P2 plus rho g y2 plus 1/2 rho v2 squared. Okay, well let's pick a frame of reference that'll be useful in determining the values of y1 and y2. Let's just make a frame of reference where we say the feeder pipe is a place where y equals 0. Then that means the value of y1 is 0, which gets rid of that term. So now we've got, in step number 2, P1 plus 1/2 rho. Now, I'm going to make a substitution for V1 based on the equation of continuity. V1 is equal to V2 times A2 over A1. So instead of V1 squared, we have V2 times A2 over A1, quantity squared. That's equal to pressure 2 plus rho g, so y number 2. Well, let's just say this. Let's make a symbol here and call it y, and in this case y is equal to h plus d. Okay, so I can drop the subscript 2 and just call it y, rho gy, plus 1/2 rho v2 squared. Okay, in step 3, let's make another substitution. Here, the pressures we're referring to are absolute pressure. So the absolute pressure at point 1 in the pipe is equal to atmospheric pressure plus the gauge pressure at point number 1. And then we have plus 1/2 rho V2, and then let's make another substitution. Instead of area, let's call it pi r squared. So pi r2 squared over pi r1 squared, and all of this is squared, equals, okay, pressure at point number 2, it's just 1 atmosphere, and that's it. There's no additional gauge pressure because, once again, when you push on the button, it opens up a valve, and the pressure absolute at point 2 is just 1 atmosphere. Okay, plus rho gy plus 1/2 rho v2 squared. We can cancel out pi, And then atmospheric pressure shows up on both sides of the equation, so we can cancel that. So in step 4, we have gauge pressure plus 1/2 rho V2, let's see, V2 gets squared, and then so does the ratio of R2 over R1 squared. So we actually get the ratio of R2 over R1 to the 4th, and then that equals rho gy plus 1/2 rho V2 squared. So let's just solve for the gauge pressure. That's the question after all, right? What's the gauge pressure in our feeder pipe? So the gauge pressure is equal to rho gy plus, here, we can factor out 1/2. What we're going to have to do is subtract this whole term on both sides of the equation to bring it to the other side of the equation. But when we do, we can factor out the 1/2 rho V2 squared. 1/2 rho V2 squared. And then we'd be left with times the quantity 1 to account for this term, and then minus, because we've subtracted this on both sides of the equation, so minus R2 over R1 to the 4th. So we got the expression that we were out to prove. Now let's apply it. So what quantities do we know? Well, since it's water, we know rho is 1,000 kilogram per cubic meter. G is, of course, 9.8 meters per second squared. Y is 1.7 meter plus 1 meter. Right? It's H plus D, as we labeled in our diagram. So that gives us 2.7 meters. And we've got the same value of rho. We found the velocity in step number 1, knowing that the water comes out of the drinking fountain in a projectile, as a projectile, at an angle of 42 degrees and with a range of 90 centimeters. That gave us V is 3 meters per second. And then we've got these radii. R2 is, well, let's see. It would be just as well if I want to change it from radius to diameter. I just double both values. But the ratio of diameter 2 to diameter number 1 is the same as the ratio of radius number 2 to radius number 1, right? Because if I multiplied times 2 in the numerator and times 2 in the denominator, 2 over 2 itself is 1, but doubling the radius gives me the diameter. So I don't have to take the value of 10 centimeters diameter and then say, okay, that means R equals 5 centimeters and plug in 5. I can just plug in the diameters. Okay, so this is a diameter of 1.2 centimeters divided by a diameter of 10 centimeters. If that bothers you, it's just as well to say, no, I'm going to make it a ratio of radii, and so it's 0.6 centimeters divided by 5 centimeters. But I think most of you see that that's the same ratio. So let's plug in and see what we get. The gauge pressure would be equal to 1,000 kilograms per cubic meter times 9.8 meters per second squared times 2.7 meters plus 1/2 times 1,000 kilograms per cubic meter times 3 meters per second squared times 1 minus 1.2 over 10 to the 4th power. Grab a calculator and see what you get. So this first term that has to do with the expression rho gy gives 29,400. Now what are the units? Let's see. Meters and meters. Okay, how about this? Instead of calling it 9.8 meters per second squared, let's call it 9.8 newtons per kilogram. Then in that way, the kilograms cancel the kilograms, and then this 1 meter combines with these meters cubed to leave us with meters squared, and now we're just left with newtons per square meter, but that's a Pascal. Okay, the second term of the equation plugging into my calculator. Hopefully you're doing the same. So the second term should give you about 4,500 pascals. So in the end, the gauge pressure is equal to about 33,900 pascals. Hard to relate to, right? I don't know exactly how much pressure that is, but I know 1 atmosphere is the same thing as 1.01 times 10 to the 5th pascals. So we could express the gauge pressure in atmospheres. So when we divide 33,900 by 1.01 times 10 to the 5th, we get a value of about 0.33 atmospheres. So there it is. We found the gauge pressure. Now I want to come back to the equation that we derived that says in a situation like this, gauge pressure is rho gy plus 1/2 rho v squared times the quantity 1 minus r2 over r1 to the 4th power. If we keep this term separate and just look at this, well, that's back to an equation we know from fluid statics that says pressure varies with depth in the case of a fluid at rest. But if a fluid, and so that's exactly what we would get if the water isn't flowing, if the velocity is 0 because it's at rest, then this just agrees with an expression we already know about fluids at rest. But if the velocity is non-zero because we're studying fluid dynamics, then this says as the velocity increases, the gauge pressure increases. In other words, if I want the water to flow out of the drinking fountain really fast, the pressure in the feeder pipe has to be higher to make that happen. So if the city engineers make the gauge pressure too high, then the speed of the water is too great, and when you push the button, prank's on you, the water doesn't come out at a typical speed, it goes too fast and goes flying well beyond the basin of the drinking fountain sink. So there you have it, just one more example of applying Bernoulli's equation.